Hello and welcome to yet another video of Cornerstones of Math. Today we will solve the following problem. Two natural numbers, m and n, satisfy following two conditions. First, m to the fourth power plus 4 to the nth power is a prime number. Second, m is not equal to 1 or n is not equal to 1. Prove that m is odd and n is even. By the way, there are many examples of m and n satisfying two conditions and the conclusion given in the problem, such as 1 to the fourth power plus 4 squared gives the prime number 17, 3 to the fourth power plus 4 squared gives the prime number 97, and 1 to the fourth power plus 4 to the fourth power gives prime number 257, and so on. As for the proof, we use the all-time famous proof by contradiction. So first, let us deny the conclusion, which is that m is odd and n is even. The conclusion consists of two statements that should be true simultaneously. So the denial of that conclusion is that at least one of these two statements are not true. That is, either m is even or n is odd. So let's divide into two cases. First case, m is even. Then we can write m equals 2k for some natural number k. This makes m to the fourth power plus 4 to the nth power equals 16k to the fourth power plus 4 to the nth power, which can be written as 4 times 4k to the fourth power plus 4 to the power of n minus 1. The parenthesis part is positive if k and n are natural numbers. So this implies that m to the fourth power plus 4 to the nth power is a multiple of 4. Therefore, m to the fourth power plus 4 to the nth power cannot be a prime number, which is a contradiction to given condition 1. In the second case, where n is an odd number, then we can write n as 2l minus 1 for some natural number l. This makes m to the fourth power plus 4 to the nth power equals m to the fourth power plus 4 to the power of 2l minus 1. And let's think about where should we go from here. Obviously, we want to make use of the condition that m to the fourth power plus 4 to the nth power is a prime number. One important property of a prime number p is that it has only two positive divisors, 1 and p itself. This means that if we express this p as the product of two natural numbers, n1 and n2, then one of them has to be 1. With this idea, let us try to express m to the fourth power plus 4 to the nth power as the product of two expressions. How can we do this? Well, this is the part where some experience-based ingenuity is required. First, I am going to take out 4 to the front, then we have 4 times 4 to the power of 2l minus 2. Then, since 4 is 2 squared, if we change the base to 2, then the exponent part must be 4l minus 4. Here I'm going to write this as m to the fourth power plus 4 times, then 2 to the power of l minus 1 to the fourth power. And this is the expression in x to the fourth power plus 4 times y to the fourth power form, which is factorable. Some of you might have learned how to do this in your algebra courses. The trick here is to add 4x squared y squared to complete the square, and thus subtract 4x squared y squared in the end. Then first three terms becomes the perfect square, x squared plus 2y squared squared, and the last term is also a square, 2xy squared. So applying the famous squared minus square formula, we obtain x squared minus 2xy plus 2y squared times x squared plus 2xy plus 2y squared. If we consider m as x and 2 to the power of l minus 1 as y and apply the result on the right, we obtain m squared minus 2 times m times the y part, 2 to the power of l minus 1, plus 2 times y squared, hence 2 to the power of 2l minus 2, m squared now plus 2 times m times 2 to the power of l minus 1 plus 2 times 2 to the power of 2l minus 2. Since this is a prime number, the smaller factor, which is this, m squared minus 2 times m times 2 to the power of l minus 1 plus 2 times 2 to the power of 2l minus 2, must be 1. We have to cleverly manipulate this expression further. And if you carefully examine the left-hand side, you will notice that we can easily apply complete the square method again on that part. So we have first two terms. And to complete the square, only 2 to the power of 2l minus 2 is required. So we write that and then write 2 to the power of 2l minus 2. So this equals 1. So the first three terms become m minus 2 to the power of l minus 1 squared. And the last term is also a square, 2 to the power of l minus 1 squared. This is in integer square plus integer squared equals integer form, which can greatly reduce the number of possible values for these integers. Here, m minus 2 to the power of l minus 1 and 2 to the power of l minus 1 are both integers, and 2 to the power of l minus 1 is positive. Therefore, the only way that this equation can be satisfied is when m minus 2 to the power of l minus 1 is 0 and 2 to the power of l minus 1 is 1. The second equation gives l equals 1, and the first equation gives m equals 2 to the power of l minus 1, hence 1. And from n equals 2l minus 1, we also have n equals 1. But this contradicts condition 2, which states that at least one of m and n must have the value other than 1. So we have drawn contradiction in both possible cases. Hence we have the conclusion m must be an odd number and n must be an even number. And that's all for this video. Thank you for watching. If you're interested in this video, please go check my other videos on a similar topic. Also, please don't forget to leave a like and I will see you in another video.